Okay, so in this video we're going to take a look at integrating factors where the right hand side of the equation involves a variable instead of a constant. So for example, if we're given that y prime plus a times y is equal to some function g of t, we can see that the right hand side of this equation is now a variable instead of a constant, because we've got a function here. So since we can't integrate this equation directly, we need to choose an integrating factor that when we can multiply the equation through by it, it'll simplify it in order to allow us to do that. So we need to pick an integrating factor, e prime of t is equal to our a times by our mu of t. Therefore our integrating factor in this example is going to be e to the at. Now don't worry if this doesn't make sense just now, because this comes from the product rule, and we'll see it a little bit later as we're going through this example why this is true. So now that we have our integrating factor mu, we can multiply through by mu. Now I mentioned earlier that integrating factors come from the product rule, and you might be able to see that the left hand side of this equation here is the product rule of e to the at times y. So we can rewrite this as this equation right here. If we want to check that the left hand side of both of these equations are equivalent, we can perform the product rule on the inner bracket here. So e to the at, the derivative with respect to t, is just a times e to the at, and leave the y there, plus, then we leave this part alone and take the derivative of y with respect to t. So we have e to the at dy by dt. And we can see that this is equivalent to this, and this is equivalent to this. So our left hand sides are equivalent, which shows further that our integrating factor just comes from the product rule. And now we can bring this dt across and integrate both sides of this equation. So we now have that our e a to the ty is equal to our e to the at multiplied by our g of t with respect to t. And if we want to be even more concrete about this, we could say that y is equal to e to the minus at times the integral of e to the at times g of t dt plus the constant that drops out multiplied by e to the minus at once we've divided through by e to the at. So if we generalize this as far as we could say that if we're given some y prime plus some, let's say, p of t times y is equal to our, let's keep it, g of t, then our y of t can be given by our mu of t to the minus 1, which is what we had here, times the integral of our mu of t times our g of t with respect to t, or mu of t times our g of t with respect to t, plus our constant times our integrating factor to the minus 1 again. So plus a constant that fell out of the integral multiplied by our mu of t to the minus 1. So if we assume that mu of t is real and greater than 0, this also means that our integrating factor will always be where mu of t is the exponential of the integral of our p of t dt, where p of t is given here. And I appreciate that that is a lot to digest, and you don't really need to remember that the general formula is given by this, because you can derive it every time, so long as you remember that the integrating factor mu of t is given by this, when our first order ODE is given in this form. So this isn't designed to make it look more complicated than it is. You don't need to remember this second part, just try to commit this part to memory if you're dealing with integrating factors quite a lot. Okay, let's try and make this a bit simpler, and we'll look at an example. Okay, so in this example we're asked to solve t multiplied by x prime plus x is equal to 4t squared. So the first thing to notice is that we don't have our equation in the standard form given up here. We have a t in front of the x prime here, whereas we just have y prime on its own here. Okay, so we could use our general solution and just immediately solve. However, let's attempt to find our integrating factor first and follow the steps. So we know already that our integrating factor is given by e to the integral of p of t dt, where p of t is just what's in front of the y here, so in this case x. So this means that our integrating factor, we'll still call it mu of t, is equal to e to the 1 over t dt, and the integral of 1 over t with respect to t is just ln of t. So this is the exponential of ln of t, so therefore our mu of t is simply t. So our next step was to multiply through by our integrating factor, so that would give us that t plus x 4t squared. And I appreciate that we're just back to where we started, however we didn't know at the time that our integrating factor was just going to be t, so this is still an important step, it can't be skipped. So the next step was just to identify that this left hand side here is the same thing as the derivative with respect to t of the product rule of t times x. So we have d by dt of t times x is equal to 4t squared. And just to verify, we can look at the derivative of tx with respect to t. So if we, using the product rule, if we just differentiate t, we're left with 1. So we have x plus, if we leave the t alone and take the derivative of x with respect to t, we have dt dx by dt, which is exactly what we have here, where x prime is the same as dx by dt. So once again, if we apply separation of variables, we can integrate this directly. So we would have d of dx is equal to 4t squared dt, and then we can integrate directly. So we have that tx is equal to 4/3 t cubed plus c, and then we can divide through by t, to give us our final solution that x is equal to 4/3 t squared plus our constant divided by t. And if we go back and look at this general equation here, we have, so our x of t in this example is equal to our integrating factor to the negative first power, so our integrating factor is t. So we have, this will be 1 over t multiplied by our integrating factor t times g of t dt, which we've worked out as, that would have been t cubed 4/3 times 4/3, so we have in fact our 4/3 t squared, and our c multiplied by 1 over the integrating factor, so c over t, which is what we have here. So like I said earlier, we could have just directly used our formula, but I would prefer to go step by step just so you understand the method, and also to save you from having to remember this hideous equation here. So long as you understand how to calculate the integrating factor, you'll be fine when it comes to problems to do with integrating factors. So hopefully this has helped somebody, and if there are any further questions, please feel free to pop them in the comments box below and I'll get back to you as soon as I can. Thanks very much for watching, and I will see you in the next video where we're going to take a look at second order ODEs. See you there.